Great. Well, thanks, Philip, and thank you to all of you for staying so late. I guess one of the advantages of being one of the last speakers is that the previous speakers have set the stage quite nicely for my talk. But before getting into that, I just want to acknowledge my co-authors and note that this work was done in collaboration or under the umbrella of CCRN, which is the Changing Cold Regions Network. And for those of you who want some more details, today I can only afford to give really a snapshot of our research because of time constraints, but it's just appeared in the Journal of Hydrometeorology as an early online release. So just to give you some background, in 2011, the Assiniboine River Basin, or ARB as I'll call it from now on, experienced an extreme and devastating flood. And for those of you who don't know where the ARB is, it's a river basin over southeast Saskatchewan and southwest Manitoba near the US-Canadian border. And also just want to give some background as to what the greater implications might be of this research. So keep in mind that this flood occurred against the backdrop of an accelerating hydrological cycle. And as you all know, changes in the hydroclimate may affect floods. And in this particular basin, where we have seasonally frozen soils and snowmelt-driven flooding, it's also applicable to other basins that are similar, such as the Ural. But it's unclear exactly how the ARB might respond to these changes in the hydroclimate. For example, it may be that certain variables such as precipitation, how they change is not as critical as the sequence of events and how those events interact. So this is the first study of its kind for the ARB, which is surprising because the basin is quite prone to flooding, and there are socioeconomic impacts associated with that flooding, as I'll show you. But it afforded us the opportunity to identify and understand the factors that are critical for modulating current and, more importantly, future floods down the road. So when we embarked on this research, we had two initial objectives, and that was to, first of all, characterize and quantify the hydroclimatic conditions responsible for the flood in 2011 and identify the key factors at play. Because if we can't understand floods now, it's not going to be easy for us to understand floods in the future or how flooding might respond to climate change. And we wanted to determine why the 2011 flood was so dramatically different from previous floods that were preceded by similar conditions. Other years had higher snowpack over the winter months, but they didn't produce floods, and other years had higher spring rainfalls, and they didn't produce a flood as large as the 2011 flood. And this last bullet here, I kind of came up after mulling our research, after it actually been accepted for publication, is to determine whether an extreme flood requires extreme precipitation. Unlike most floods that we're familiar with, this wasn't a single precipitation event that led to the flood. And these are some pictures from the 2011 flooding. You can see the farmer there. In 2011, it's estimated that over 5.5 million hectares of land did not produce crops that year because of the flooding. So to study this event, we had to draw on a really diverse set or range of data sets because no one data set obviously could satisfy all our needs. So just before going into some of the science, I'll talk about the significance and impacts, but also give you a bit more information about the ARB. It's a relatively small basin. It's about 160,000 square kilometers. It doesn't receive that much rainfall, between 400 and 500 millimeters per year, and about 100 centimeters of snowfall. So it's quite strongly driven by the spring snowmelt and the spring freshet, as I said, during the spring months. And what's also fairly unique about this basin, it falls in the prairie pothole region. And because of that, it's got a very large storage capacity. And unfortunately, that pothole landscape also complicates the hydrology. So as some of the other speakers were saying, duration was really critical in this flood. It was of unprecedented duration and impacts, at least for this period of record, which is about 100 years. And one example of that is that one of the stream gauges, which is Brandon, which is the red dot over there, they exceeded the flood stage for 110 days. So as you can expect, with that kind of flooding, the impacts were quite significant. There was critical damage to infrastructure, such as roads and bridges, and over 7,000 people were displaced. which in the greater scheme of things may not sound like too many people, but keep in mind that this is a basin with relatively low population density. And the flood caused well over $1 billion Canadian dollars in damage. And what's surprising to me especially is that, of course, there were significant socioeconomic impacts, but those are still ongoing some 4 years later. So just let's place 2011 in context. Prior to 2011, the data show that the next biggest flood, or the previous record flood, was 1976. And that's the purple trace here. What we're looking here is the accumulated discharge in cubic decameters. And the red trace here is the accumulated discharge that's typically experienced over the basin. And this is another flooding event in 1955. So you can see by all accounts, this was a really significant event and well worth looking into. For example, the discharge at Headingley, which is at the terminus of the basin, was 4 to 6 times greater than its annual total. And just going back in the record, we're lucky that we have records going back to the early 20th century for this basin, and you can see once again, although we have had floods, it is prone to flooding, this basin. This is 1976 over here, but the accumulated discharge for the calendar year in 2011 was quite remarkable. Depending on what assumptions you make with calculating return periods, you get about 230 years, but some estimates go as high as 300 years. And as I mentioned earlier, the flood was of unprecedented duration. This is for a site at the Headingley site again. And what we have here is 2 years back to back. So the climate is this dashed line, and you can see the spring freshet when we get the snow melt in the spring, and then it slowly decays after that to really low flow during the winter months. These blue lines here are before 2011, the maximum record discharge for every month in cubic decameters. And you can see in 2010, originally the flow was below average, and then we had heavy rains in the late summer and into the fall. So going into the winter of 2010, 2011, the river was already flowing above average. And then after the spring freshet, we had these heavy rains, and I'll speak to those in a little while here. And then we had this prolonged period of really significant discharge and flooding, and which is way above the previous record for several months back to back for this basin. So looking at the antecedent soil moisture and snow water equivalent conditions, here we are looking at data from the JRA 55 reanalysis. The reason we chose that analysis is that it goes further back than the satellite era, so we could go as far back as 1958, because unfortunately there were no significant floods during the satellite era that we could compare with. So this allowed us to look at the 76 flood. And what you see here, these bars, these are the standardized anomalies in the top 50 centimeters of the soil. And in the fall of 2010, and then for the year between May of 2010 and April 2011, we can see that soil moisture was really high, more than 2 sigma higher than average. So the soils were obviously quite saturated. And then looking at the SWE over the basin, this is from the glob snow product. This is the March SWE anomaly in millimeters. And again, March SWE was very high. So the stage was set for high discharge or possible flooding in March or April because of the heavy snowpack. But of course, there are other years, like here in 1997. For example, why did that year not produce a flood? So we wanted to look at that, and we delve into those details more in the paper. And then just looking at the spatial distribution of SWE over the basin in that March, typically over the basin in March, we have about 30 millimeters of snow water equivalent from the glob snow product. But for this year, March 2011, most areas were greater than 60 millimeters, so about double. So that was the setting, and what really changed was the atmospheric forcing in May and June of 2011. Now, I don't have time to look at all the parameters here or the data for May, but if you look here, these are the mean maps for June 2011, and this is just setting the stage for what happened, as you'll see in a few minutes here. We had a mean long wave trough over the west coast of North America. And here's the Assiniboine River Basin in red. And this was downstream or downwind of that long wave trough. And what this long wave trough was doing was spinning off shortwave energy. And if you look at the surface pressure maps, there was a negative mean sea level of pressure anomalies here as a result of cyclogenesis. And not surprisingly, with that setup over the basin, we had strong mean vertical ascent over the basin. And as a result, we had heavy precipitation association with that. So the key thing here is that there was a very persistent large-scale circulation pattern that favored increased cyclogenesis and cyclone activity in May and June in the vicinity of the ARB. Now, this is just showing you the rain for May. These are percentage anomalies. So in May, large portions of especially over the southern basin, had up to 200% higher than normal precipitation. And then going into June, those rains just continued, and they weren't quite as significant as in May, but we're still looking at 150%. And the yellow dot here is a station at Estevan, so let's just drill down in the data. And here we're looking at the accumulated precipitation using daily data from Estevan. And we can see this here's the red, so not surprisingly, these are flood years we're looking at. They're above the climate. But focusing on 1976 and 2011, you can see up until about 1st of May, 1976 and 2011 were almost the same, yet 2011 ended up producing twice the accumulated discharge than 1976 did. And what we'll see is there was this critical period in May and June where you can see the steps in the data here as we had a really, quite sequence of heavy events shortly after one another. Whereas in 1976, there were pretty good rains, but they were nothing in comparison to what happened in 2011. And if you look at a Hofmöller plot here of the daily outgoing long-wave radiation anomalies, this is the longitudinal band where we have the ARB. And these red squares, you can quite nicely see the west-east systems traversing the basin and producing the heavy rainfall events. So this kind of synoptic setup was quite critical and quite interesting. Unfortunately, we didn't have time or space in our paper to dig into why that was the case. And the last thing we did was to try and tie all this together is that we did a terrestrial water budget analysis using the JR55. We did do some validation and found it was in good agreement with observations and other reanalysis products like the ERA interim. And I won't look at all the terms here, but here's we have the delta SWE contribution. And for simplicity, I'm just looking at 76 and 2011. The black line here again is what you can expect. And you can see in 1976, remember that year had quite a substantial snowpack. We had the rapid melting in the spring with the thaw, and then things taper off obviously once all the snow's melted. But in 2011, we had an unusually cold March, and what that did is it delayed the spring thaw. And interesting enough, the runoff, or not the runoff, but the contribution from the snow melt was not as significant in 2011 as it was in 1976. So going to precipitation, I won't speak too much about that because you just seen that graph. Another interesting thing is the evapotranspiration in 1976 was quite a bit higher than it was in 2011. And what it meant in 2011 is that the evapotranspiration was lower, so there was little time for the soils to dry out. And because the freshet was delayed because of the cold spring, as the streams were peaking in their discharge, that's when the heavy rains in May and June started. So it was really an unfortunate sequence of events. And it's reflected here in the runoff that you can see initially in 1976, it was quite a high discharge as that heavy snowpack melted, but then it plateaued. But in 2011, it just continued to rise because of the heavy rainfall in May and June. So it was a sequence of events that really were critical here. So just to finish up, that graphic up there is meant to illustrate the impact of compounding or cumulative effects. This isn't your typical flood when you have one rainfall event and you have a flood. It was the sequence, timing, and magnitude of events going back to 2010 and their cumulative impact that were critical in bringing the 2011 flood to be realized. And we also found that the delayed freshet followed by heavy precipitation in May and June were key in differentiating 2011 from 76. And just to think of it in a bigger picture about these events, one typically expects an extreme flood to be associated with extremely high SWE or extremely high precipitation, but that was not the case. Although they were very high, they weren't the highest necessarily in the record. So this does corroborate the thinking that compounding impacts from a series of events can lead to extreme natural hazards. And just thinking in a bigger picture, one possible implication of this is that while there has rightly been a lot of focus on extreme events and how they're changing, even shifting the precipitation PDF towards heavier but not necessarily extreme precipitation events could lead to an increase of extreme floods, especially in basins like this where we have a high storage capacity. Thank you.
Thank you very much for the talk. We can take one quick question, if there is one. Mark.
You were, at the beginning of your talk, you were talking about what we call a pothole landscape.
Yes.
Which I assume is glaciated, previously glaciated with maybe hollows that may fill with water.
That's right.
Or snow. So was the amount of storage also not larger than an average at the onset of, say, the rains?
Yeah.
Because of the previous. So was there any storage effect in that sense? That the whole thing was already saturated or full?
Yes, to quantify that's difficult, but given the high soil moisture and the heavy precip, it was probably that the storage capacity was maxed out going into the winter, so there was really no room come spring.
Thank you very much.